I think I'm introducing myself um, for this section. So, what we're going to talk about this morning, myself and Sean Dubé, who we're both working on looking at dark matter data associated with the LZ experiment. This particular working example is using entirely simulated data, but what we're going to do this morning is in line with the previous working sections or modules. We're going to talk about the physics and one or two other observations, or sorry, comments surrounding that. We're going to talk about techniques in machine learning. And I think Sean and I and others involved with this, who I'll mention a bit later, we're really trying to make this particular worked example as accessible as possible. Uh, uh, Very deliberately, the notebook that you're going to be working on in an hour or so has parameters that are missing, currently have question marks in them. So the idea is that you're actually going to, I hope, pick up enough from our discussion ahead of time, and as Sean takes you through the notebook, that you get a strong sense of how to fill those parts of it in. I think the other uh, sort of worth mentioning is that while the net is sort of being optimized in a fairly sort of standard way, it is always the case that the actual overall structure that you use to approach a given problem, it can be quite challenging always to the methodology that you're going to use to figure out what is an optimal network strategy. So there can be, and there often is, a lot of trial and error. I think one of the things you're doing as as individuals, you become more sophisticated in terms of your understanding of how to work with neural net. You'll get a better and better feel for what is optimal. I will say, the last, 5+ years of working on these types of approaches, I'm always a little alarmed if we get to the point where we're a little too random, should we say, in terms of the things we try. I always try to motivate students to make sure that they have a sort of fundamental understanding of the various mathematical functions and processes and computing sort of schemes that they're using to process data. Having said that, I think we all also recognize that machine learning approaches do sometimes lead us in directions that we didn't necessarily expect, and kind of in a good way. So we're as physicists, as scientists, we're trying to get this balance. But let me start sharing my screen and run through um, the slides that we have prepared for this discussion. Okay, so as I mentioned before, we're going to use the physics experiment, the LZ dark matter experiment. Uh, there are a group of us here at Brown in the particle astrophysics group, many of whom are listed on the slide I'm showing you here, and I include our contact details at the end of all of our contact details at the end. If anybody has sort of physics or machine learning questions that they would like to extend beyond, beyond. Uh, and during this session, please feel free to ask questions using the chat system or the Q&A system in the Zoom. My colleagues are keeping an eye on that, so they will interrupt so that relevant questions can be addressed during the presentation. So if we, I just thought, partly because it's not always completely universally common knowledge, but I decided to throw up or put up the prefixes for the System International, the SI units. Obviously, they are designed to step every 3 orders of magnitude, and I realized during our preparations for this that the conjunction of the various material we're talking about in this session combines. We use virtually every prefix you can see here, certainly the ones that are, three orders of magnitude separated, the most common ones. I think we've managed to get prefixes all the way from exa, which is 10 to the 18, all the way down to yocto, which is 10 to the minus 24. Uh, as I often discuss with students, this is why it's so important to use in physics logarithmic graph or logarithmic axes when displaying data. Linear barely does anything. We work in justice, and also so often we're interested in ratios, which come out directly from logarithmic graphs rather than simple additions. But let's, have a look at this in a bit more detail. And I think one of the, as I say, when trying to sort of give us, why are we sitting here today talking about, machine learning in the way we are? I mean, I will say over my entire scientific, career, right from when I was like sitting as a graduate student, machine learning has been a thing. It's just we were conspicuously, should we say, or rather limited in our success in using it. I did work with a student back in 2001, 2002, where we did demonstrate machine learning, but it was hard fought. And the point is that the ubiquity or the ready access to significant amounts of processing power has really made it very productive at this point, and will continue. This approach is going to continue to be extremely productive. So, just consider if you go back to 97, that was when the first supercomputer, this one happened to be at the DOE Sandia Labs down in New Mexico, Sandia Labs down in New Mexico. It cost about $70 million, and it was known as ASCII Red, and it crosses the 1 teraflop. So that's the 10 to the 12 floating operations per second. This is one of the metrics that's used for these machines. Now, within, say, of the order of sort of 12, 10, 12 years, the best supercomputer crosses the petaflop. So we're now 10 to the 15, 3 orders of magnitude more capable. And then, another 12 years later, we actually have crossed the exaflop, which is 10 to the 18. So that's another 3 orders of magnitude. So every sort of 12 years, you can see this factor of 1,000 improvement in supercomputing. And this is often called, referred to by Moore's law, given that, we are interested in how much processing we can reasonably get for, I mean, these are quite large sums of money being spent, but nonetheless, it's a similar amount of money each time that is buying a more and more capable processing. Now, I think one of the things that's incredibly sobering, and again, will make you realize why machine learning is becoming so ubiquitous, is that, of course, in 2020, for instance, the iPhone 12 actually started, was delivering 1 teraflop. So that was in a period of, say, roughly 24 years. We have seen a 10 to the 5 reduction in the unit cost. So it's not quite the 10 to the 6, but it's a 10 to the 5 cost in compute. And that, if you think about it, that is an extraordinary amount of processing that you're carrying around. And of course, this characteristic improvement and our access to processing is going to continue. So let me talk now about dark matter. The missing mass of the universe, the dominant 85, what we think is 85% of the missing mass, or sorry, 85% of the mass of the universe. I say missing, and the reason it's called dark is because unlike most of the material, conventional material, which interacts with photons and allows us to use conventional, telescopes, albeit spanning a huge many orders of magnitude in terms of wavelength. The dark matter is much more weakly interacting if our hypotheses are correct. So we measure that cross section, the probability of interacting in terms of a physical area, and the most obvious SI unit would be meters squared, although as you'll see, we've actually introduced a number of sort of stand-in units for measuring area. The most obvious One or the most commonly used one is actually the barn, which is indeed named after the barn door. A little bit tongue in cheek, as so many things in particle physics in the last sort of 30, 40, 50 years have been. But the barn is actually 10 Fermis by 10 Fermi. So a Fermi, as we'll see from our SI, is 10 to the minus 15. So it's 10 to the minus 15 meters, but it's 10 Fermis by 10 Fermis. So what we have is about 10 to the minus 28 meters squared area. Now, one of the peculiarities, I'm afraid, of particle physics is that it still uses centimeters, not meters. So you will so often see if somebody's quoting a cross section, you'll actually see them talk in terms of centimeters squared. So it's 10 to the minus 24 centimeters squared. Now, just to give you a sense of where we are with particle dark matter searches, if we use this barn, I'm going to stick with the barn unit. We When we first conducted searches looking for particle dark matter, we would have been sensitive to, and I'm afraid I'm venerable enough to have actually been involved very shortly after this first experiment to, actually looking for these events. But this is at the 0.1 femtobarn level. That's a measure of the cross section or probability of interaction between conventional matter and the dark matter itself. And if the dark matter had been interacting at a strength above that sort of 0.1 femtobarn, we would have been started seeing events in the detectors we have. If the cross section was less than that, then the other events, the sort of more conventional random backgrounds in our detectors would have covered the signal. So we were basically what we would refer to it as sensitive at the 0.1 femtobarn level. Now, wind forward, and I can only really talk about sort of a couple of milestones, ones that I'd been directly involved in, but we actually joined in 2013, so 10 years or so ago. We finally joined Club Sub-Zepto, and by that, what I mean is that we actually became sensitive in the what was back then the Lux experiment. It was about a third of a ton of xenon. We would have been able to directly see dark matter particles were they interacting at a cross section of around a zeptobarn. Now, I don't have time to sort of explain why we have such significant uncertainties in dark matter cross section interactions, but suffice to say that the way that cross sections are formed, it's very dependent on what the coupling particle is that it goes between the dark matter and a conventional target. And there's a 1 over mass to the 4th dependence on that particle, that gauge particle, the coupling particle. And since I'm afraid we are still relatively, we haven't been able to pin down what the exact particle physics model is that creates the dark matter, and therefore we still have to allow for significant uncertainties in the coupling particles, and therefore very significant uncertainties in the actual overall cross section. Now, if we run forward to last year, the LZ, the Lux Zeppelin experiment, announced what is the world leading sensitivity, and it's actually got down to 100th of a zeptobarn at this stage. It's not the only experiment looking for dark matter interactions directly, but that we are beating in terms of rate of progress. We're taking less than 12. We're only taking about 10 years for a factor of 1,000 improvements. So we're beating Moore's law within this search, this dark matter search, and we intend to continue doing it. And we're going to move down into the sort of Yocto-Barn region, and at that point we sort of run out of prefixes. But let's look at AI and what are the appropriate units. So we have, we were talking about the flop and the barn as these measurements of progress in looking for either raw processing power or cross sections. But let's consider for a moment in AI. Now that I'm not sure there is a sort of standard unit there, but let's put our tongue a little bit in our cheek and talk about an appropriate unit. And I think you could argue that Sapien, or the Sapiens, is an appropriate unit, which is a sort of good human level of competency. How is AI doing in a particular area, or possibly even a general area? How well is it doing? And how do we how do we refer to that? It's either the SP, or let's really put our tongue in our cheek and call it the force, the old SAP, sapiens, the union. So one sapien would be competency in a given area. Or, as I say, we do want to look at, with AI, at artificial general intelligence, AGI, um, and more on that in a moment. But let's start off with chess, which is something I certainly, grew up with in terms of interacting not just with humans but also with machines. And I do remember my own high school experiences in the 70s that we had chess computers, sort of dedicated hardware, but affordable dedicated hardware. But those really played at a level compared to a sort of, certainly if you're going to use a grandmaster as your one sapiens thing, they were in the nanosapien or millisapien or sap level. Of course, what happened, for instance, in with great media and wide focus, was that by 1997, a dedicated large machine known as Deep Blue actually completely destroyed, I think, unexpectedly, but Garry Kasparov, the Grandmaster world champion, and that really set barely 5 years, and then at that point people just stopped competing with computers. There was just very little point. Computers continue to compete with one another, but they're playing so much better than or better in the sense of winning games than the humans. And of course, again, as we saw with the phone, the iPhone versus the supercomputers, by 2002, standard commercial computers are playing better than one Sapiens, if you like. And I think many of you may be familiar with the sort of recent history is, of course, a change in the way that AI for playing chess has been designed, which has just dramatically brought down the amount of training required, and that we're at the level where you can achieve, if you like, killer sapien levels of proficiency, based on, it gets difficult to rate the chess playing efficiency, really, because the ratings were based on humans, and the machines are playing so much better. But in 17, we're seeing Alpha Zero with less than 24 hours of training, playing at incredibly proficient level. So my alarm just went off, because I know that the Japan are about to land on the moon, but I guess we'll have to stay focused here, and then in about an hour and a half we can all see how their landing went. But anyway, so 2017, 2019, Mu Zero doesn't even need to be told the rules of chess, just observes chess games and goes on and nails them totally, and with less than a day's training in any of these things, and doing the same thing in Go and chess. So you're seeing this exponentiation, these orders of magnitude achieved, and of course, from here on out, you can imagine what it means. And I will, again, tongue firmly in the cheek, say that, well, what happens when you have, say, a killer sapiens of AGI, of this artificial general intelligence? Is that the point when AGIs really become, especially if they're ubiquitous, they start becoming somewhat troubling? And the question is, what is the unit of lethality if you're talking about bad AGI? And I think, certainly if one goes with the old school cinematic representation, that the unit has to be the Schwarzenegger. I don't know how you abbreviate Schwarzenegger, but let's say if it's one's SZ, then maybe, we have to start being very careful when we hit Killer Sapien AGI or Kilo Sapien AGI, because we will be in the Schwarzenegger regime. But anyway, let's go back to the physics now, and look at this LZ, the Lux Zeppelin dark matter experiment. It uses a large liquid xenon. How large? 10 tons. It's this huge, it's sort of 2 meter scale in linear dimension target of liquid xenon, or sort of 1.5 meter, 2 meter to the sort of edge of the containment, the first containment vessel. And it's been built by multiple institutions, physically all over the US, including here at Brown. And I can show you a few photographs just to give you a little bit of a sense of what it means to do this kind of physics. And it was assembled deep underground at Sanford Lab. I won't go into why deep underground, other than to say we are looking for somewhere very quiet. to operate the detector, and we need to put about a mile of rock between us and outer space. Otherwise, all of the cosmic rays, particles coming in, secondary cosmics, are just going to make such a search for the dark matter particles, which are very penetrating and don't care about a mile of rock. It makes it thing. And we've been operating it since 2021. And again, we've built up huge amounts of data, both from the detector. I think we're well over a petabyte. So you'll remember, we've got giga, we got tera, we got peta, petabytes. The relative cost now of storing a petabyte and processing a petabyte, runs to tens of thousands of dollars. It's not actually, it's an extraordinarily large amount of data, but in modern terms, not price prohibitive for scientists to be working with that kind of thing. And what we're going to do is take our example from event reconstruction, and we're really going to simplify it. Sean and I, and Austin and Chen, who've all been working on this, we try to boil it down to a very simple example, just to give you a sense, and I hope it'll be one that you can completely understand every step, and therefore you go away from this meeting with or this workshop with a, emboldened in terms of your willingness to get involved in using machine learning techniques. Not to the exclusion of all other techniques, but just put them in your toolkit and know that you can use them. So this actually here is a photograph of the group, and actually under that silver bag was a piece of LZ about 2.5 meters high, and actually that was the first of two pieces of that scale. And I think on the next graphic, yes, I do. It's actually this thing. This is an array of photo multiplier tubes, photodetectors, single photon sensitive, that we use to watch the xenon target, in order to, when the interactions occur in the xenon, they actually give away a signature which is associated with light emission, as I'll show you in a minute. And it's going to be those light emission profiles that we're going to study, in our workshop example. So we shipped it from, as many other groups did, but we shipped our large pieces from Brown to Sanford Lab because we have constructed an underground laboratory a mile down in the Black Hills of South Dakota, where previously gold had been mined for. We're using that same infrastructure now to do science, dark matter science, neutrino science, and thing. It's Sanford Lab. If you go to sanfordlab.org, you can get a pretty good idea of all the science that's going on there. And I include even a photograph of a chap skinny dipping in a water pool, which is actually now the cavern that we are actually operating our experiment. But this is Ray Davis, the Nobel Prize winner, who discovered, not only was able to sort of directly detect neutrinos coming from the sun, but of course, as many of you might know, started in the 60s, and it became pretty clear that we weren't seeing in his experiment, he was not seeing the expected number of neutrinos from the sun, which of course led to some question marks as to whether we misunderstood the sun. But it turned out, no, we understood the sun well. It was the neutrinos themselves were oscillating, and of course this continues to be an area of significant study. And we are now sending a beam or beams from Fermilab, neutrino beams, through Minnesota or underneath Minnesota, and appearing actually at Sanford Lab, and will be measured directly there in order to study neutrino properties. But so by being a mile underground, we're reducing the flux of secondary cosmic ray muons. That if you're here on the surface of the Earth, about one every second is going through your hand all the time. Whereas if you hold your hand out a mile down, it goes to about one a month level. You're talking about a factor of a million reduction in the flux. Now the detector itself, for scale, we're looking on the left at something that's about 2 meters high. That represents, I think, inside that white cylinder is 7. Will not in this point, but it will shortly. when the detector was all closed up, there would be 7 tons of xenon being watched inside that. And what we've done is put these arrays from Brown, shown bottom right hand. You can see all these photomultiplier tubes staring down at the xenon and also staring up at the xenon and looking for particle events. Now, in order to sort of make the signatures extremely useful, what we do is we apply a field. So you'll see top right is actually a woven transparent mesh that goes over the PMTs so that we can strike a voltage between over a distance of, say, 1.5 meters. We can strike a voltage differential that is designed to have electrons drift directly through the xenon. So, and you'll see the consequences that additional drift term has in the signal shortly. And our goal really is to create the quietest place in the universe at low energies, and we're trying to look for extremely rare events. And the xenon is a good target for this because it's very low in intrinsic radioactivity, and we've worked very hard to keep out external cosmic rays going a mile underground. We've also, as you'll see in a moment, immersed the whole system inside a very high purity water tank that's some 8 meters in diameter, again, to keep out conventional gamma rays from conventional, natural radioactivity. Now, the bit that we want to understand for this workshop is shown here. So on the left, we have sorry, just going back. On the left, what we have is an indication of if a particle were to interact in the middle of the xenon, two things are going to happen. You're going to generate some light from the scintillation processes, the temporary excitation of the disruption of the xenon and de-excitation, multiple atoms involved. They're all, although the initial energy is deposited by interacting with a single atom, depending on how that energy is imparted, it will spread to other atoms, and you will see light being emitted. And we call that an S1 pulse, but just first pulse. And it's a very short 200 nanosecond burst of light. It's shown in this inset as an S1 light signal. And then if you wait some time, because we're applying a field to this xenon, the electrons are drifting upwards from the interaction site at a velocity of about 1.5 millimeters per microsecond upwards to the top of the liquid surface, because the liquid surface but through that grid is designed to be more positive. So electrons drawn upwards. When the electrons arrive at the liquid surface, they are extracted from the liquid. And one of the fascinating condensed matter effects that we exploit, of which there are many, is that when electrons drift in liquid, they do so in a way that is non-radiative. They do not emit any kind of additional light. So we only get a pulse of light from the initial interaction, the very non-equilibrium physics that's taking place there. But after that, the electrons, having been created and being drifted, they do not emit light until they jump from the liquid into the gas, at which point their transport becomes radiative. And we see a burst of light associated with the electrons moving now in the gas. And they basically move from one grid, which is just at the surface of the liquid, to another grid some centimeters above that initial grid. And during that period of drift in gas, they emit a significant amount of light. That second pulse is known as the charge pulse, or the S2, but it is now a light signal. It is detected by the PMTs associated with the electrons moving through the gas. We're not measuring the charge directly, but we are measuring the light emitted by the electrons that are traveling through the gas. So you've got an S1, then no signal, and then an S2. And of course, the time it takes between the S1 signal, the initial flash of light, and the second flash of light tells you how far the electrons had to drift, what time delay was there. So we use that time delay to tell what the depth of the event is. And the electrons also drift directly upwards. So the XY position of this hotspot of emission tells you what the XY position of the interaction must have been. And you can do this with a single electron. A single electron can come and it lights up sufficiently in the gas to be very measurable. Most of the time, we're measuring multiple electrons, tens of electrons, hundreds of electrons, or each of which is radiating light in the gas and produces a hot spot that I'll show you some examples of in a minute. So that's it. Now, plotted on the bottom right is an example of the primary light, the S1, and the secondary charge light, S2, for events that are associated, for instance, with electron recoils, such as a gamma interacting deep in the xenon, causing an electron to recoil, or in the case of the red or the lower distribution, a nuclear recoil event. And the easiest way for us to create that is actually using a neutron. We have a neutron source or various neutron sources, and a neutron will go into the xenon, will bounce off a xenon nucleus, and will again cause both primary and secondary light. But it turns out the ratio of the two is somewhat different, and by that allows us to tell the nature of the interactions. So I hope this next graphic really, because it's important you get this. We have this initial 200 nanosecond burst of light, then we wait for the drift time in time, and then this S2 ionization signal. Now, the workbook that you're going to be doing is focused entirely on the shape of the S2 pulse, because I think I hope you can get this sort of immediately. But if you imagine the incoming particle scattering from a xenon and then outgoing, imagine if that particle interacts not just once, but twice fairly rapidly in succession. That will actually mean you have two charge bursts or two charge clouds, which may be quite close depending on the nature of the interaction. So you end up with two S2 envelopes that overlap one another. You are correct in thinking, but Rick, doesn't that also mean I'll see two S1 bursts? But the fascinating thing is, of course, the initial particle is moving so rapidly. If there are these two scatters, the amount of time between the first interaction, the second interaction, in terms of generating the burst of S1 and then another burst of S1, they'll basically lie over one another, because a particle that's moving, if it's a photon moving at the speed of light in a single, in 1 nanosecond will go 30 centimeters. So, and the physical dimension here is about equivalent to light passage time of 5 nanoseconds. So given that the S1 light structure has about 200 nanoseconds as its width, it is difficult to use S1 substructure to see the delays. But because the electrons drift much more slowly at millimeters per microsecond, the S2 structure will belie if there is a multiple depositions in the S2. And why do we care? Because some of the rare events we're looking for actually do have multiple depositions. But also when we look for dark matter, one of the key signatures for dark matter interaction, if we're looking for that type of rare event, is it's actually a single scatter. Dark matter interacts very rarely, but so we are looking for single nuclear recoil events in the detector, and that's very much the spirit in which we're going to do this. The example. So I should mention a little bit about dark matter in case you're a bit rusty. But the model we have for the universe, and I like showing this one because, again, when I was sort of just starting as a faculty here at Brown, the numbers that applied the universe had about 73% dark energy and about 23% dark matter, something like that. The numbers have evolved. We're at about 69% now dark energy, 26% dark matter. So that gives you an idea that over the last 20 years, our improvement in our ability to model the universe has been at the few percent level, and the uncertainties now in the dark energy and the dark matter numbers are at the sort of sub-percent level. Now, of course, when I was sitting where you are, as if you're a graduate student, in fact, although the idea of dark energy was a possibility, it was certainly not a favored one. It was, in fact, extremely unfavored, and we thought that dark matter was the majority of, basically made up everything beyond just the conventional material, the stars, the intergalactic gases, and what have you. That is often referred to as baryonic matter or conventional matter. Anyway, we're really looking for this 26%, the modern numbers, these ones in the white boxes. Those are the sort of modern numbers we're doing. And what we're trying to look for very specifically is a dark matter particle that comes straight through the detector. Most of the time, we're talking about tens of millions of dark matter particles just through your hand every second, if the hypotheses are correct. But the cross sections are these Zeptobarn, yes, we're on to Autobahn levels, and we're really just looking for a single, very occasional dark matter particle that scatters from a nucleus. Now, the backgrounds are, for the most part, electrons and gammas that were emitted by more conventional forms of radiation, but they interact with the electrons. So one of the key properties of xenon is that it can differentiate between a nuclear interaction and a beta interaction. But the event rate we're typically looking for dark matter particles is, even in something that's 7 tons of active xenon, we are still searching for many weeks or months for a single interaction for the dark matter in order to be able to test these dark matter models that are currently the ones we're able to test. So another way of visualizing, if you like, or getting a feel for what a 10 to the minus 47 level in terms of the centimeters squared, if we work in those units, cross section, that's basically where we are now. Our current physics testing is testing at this 10 to the minus 47 square centimeter level. That would be equivalent to taking one dark matter particle and squirting it through lead. If we stacked lead all the way from here and frankly went past Alpha Centauri, went on about 10 light years, so it's double that distance, the dark matter particle would still have a 50-50 chance of coming out the end without having interacted in that stack of lead. It is that the interaction is that weak. Now, because there are locally here in this room, in your room right now, 10 to the 7 dark matter particles per hand per second, even with these crazy small cross sections, we still will get a finite interaction rate, but we do have to wait weeks or months, and we have to do so ensuring that we can eliminate all other more regular, boring processes and look for just the individual dark matter particles. Now, I think I prepped a few photographs here, but I think we've done enough discussion. I would like to oh, sorry, this, I hope you can see this, but this is a video of actually traveling. We don't always travel, by train through this sort of these type of areas, but when you are underground, it's always quite fun to occasionally sort of explore some of the most of the lab we work in is completely finished, and it's just like working in a regular lab. Of course, you are just a mile underground. But anyway, yes, I think what we do, I really want to talk about the workbook now, or the workshop. So let me show you what some of these events look like. So we're going to talk about S1 and S2. But the final workbook will just focus on S2 events. But here, for instance, on the top left is a single photon creating a single photoelectron in a photomultiplier tube, which is quite extraordinary. This is a quantum sensitive array able to see single photons from the UV. Now, also rather extraordinary, bottom is what happens if a single electron in this 7 tons of xenon is liberated, and we can extract it, we can drift it and extract it with extremely high efficiencies. When it jumps out of the liquid into the gas, it produces this S2 pattern, this secondary pattern shown in the bottom left. And each of those spikes you're seeing there is a photon that has been converted in a photomultiplier tube. Now, we're adding together all of the signal from the many 500, basically, photomultiplier tubes that are all looking at this xenon. But that's what a single electron looks like, which is an extraordinary feat when you think about it, and is fascinating. And before you say, hey, Rick, how the hell can you count single electrons? Remember that the xenon is at about minus 100 degrees centigrade, 160 Kelvin, say. As a consequence, thermal emission of electrons is sufficiently suppressed that we really do end up with this incredibly quiet space in which even the generation of single electrons is a special event, and we're able to sort of measure all of these occurrences of individual electrons, or in the case of particle interactions, it's usually generating multiple electrons. So here on this slide, actually showing what it looks like where you break down on the right, you break down the signal into the top and the bottom array. The top circle and the bottom circle in each of the pairs of events here is showing you what the hit pattern looks like. And initially, we're talking about the S1 event, which takes about 200 nanoseconds. And it is mainly collected in the bottom array because of total internal reflection on the top liquid surface. Most of the photons end up in the bottom array. But then the lower half, we have what the S2 event looks like, which varies in width, but say 2 to 4 microseconds wide. And the critical thing I want you to be aware of is that it focuses the energy, as you can see in the lightest colored PMTs. Those are the ones that are being hit very heavily. It's a logarithmic scale. You have a bright spot in the upper array, just where the gas that got lit up by the electrons that went from the liquid into the gas. So we can use that sort of concentration to study these guys. So we're going to focus on these S2s in the workshop. We're going to just ignore for our analysis the S1s. So here, for instance, is in as a snapshot over say 40 microseconds is an interaction that occurred at energies that are consistent with a WIMP signal. Although I can tell you this particular event is because we had a neutron source, which creates a nuclear recoil very much like a WIMP in the detector. But what you're seeing is a little burst of initial S1 light. You then wait for the electrons to drift, and then you see the S2 light happening after there. And the signal to noise, the sort of jiggedness, is because we're counting photons, and so it's the Poisson fluctuations in the photons that give the sort of jiggy, the apparent up and down. And that, if you like, is your limiting for the events that you're going to be working with. It's that fact that they are represented by individual photon counting that gives some uncertainty. So if you're trying to, as we are going to be looking at the shapes of the S2s, this is the sort of challenge. I think I'm going to so this is the meat of what the exercise we're about to do. On the right and on the left are examples of S2 pulses, which are of the order of sort of 2 microseconds wide. But these are actually S2s which are composed of 2 individual energy depositions, but close enough physically that the electron clouds, as they arrive in the the liquid surface, that those distributions are overlapping. So usually for a single event, you get a sort of a Gaussian-like envelope. Now you've got 2 Gaussian envelopes added together. And we're going to use machine learning to try to differentiate those. Now, using conventional technology, we differentiate by using a sort of maximum likelihood or chi-squared inspired fitting with 2 hypotheses, a single Gaussian or a double Gaussian with some separation that we're attempting to establish. And that is very much the sort of, the conventional way that you would do it. But what we've also done, as you'll see with your workbook, is we're going to, rather than telling the network that the world is Gaussian and what have you, we're actually going to give it single scatters, and we're going to give it events like this, which are multiple scatters, 2 events occurring, we call it an event, but 2 vertices, 2 hits occurring, creating 2 Gaussians, which have been co-added in the S2 due to the 2 energy depositions close door to one another. We're going to just ask our network to learn the maximal way to differentiate between the 2 and produce an output which tells us whether it favors the single hypothesis or the double hit hypothesis for the particular S2 signal that you've given it. Okay, so the difference in approach here is that traditional data analysis, we form hypotheses for the way we think all the mechanisms work in the detector, and then we form a sort of test statistic, if you like, based on those sort of hypotheses. And often we are doing some sort of staged of reducing what initially the time traces will measure things like the pulse area or the pulse rise time or the pulse width under a Gaussian hypothesis or some other hypothesis, and we will extract numbers associated with those fits, and we will then try to combine that. And often you have to then combine lots of those new parameters in ways to try to determine what the underlying physics of the interaction was. Or we can actually go at the problem a different way, which is rather than trying to pick it apart and do these functional analyses, we start, if you like, with almost the sort of boundary condition, which is what the events themselves are, and then we put it all through a machine learning, some kind of network. We'll talk, about CNN, convolutional neural net, and we'll talk about, sort of deep layer decisions, for this particular example. But essentially, we will simulate events, or we will use calibrated data where we have enough. A source which is pure enough creates a particular type of event, and we use that to sort of train the net, and we then ask the net to look at other events and from our detector where we don't know what they are, and ask the nets to sort of score them or classify them and decide, is this event sort of consistent with a single scatter in this case, or is it more consistent with a multi-scatter, as a classification example. Now, I put in the deck two specific areas. There's many more slides here than I can talk about, but I do find in talking to students that these concepts get thrown around, and I just wanted to make sure you give yourself enough time to understand these two particular sort of mathematical relationship. And I've tried to explain them in more visual terms, if you prefer that, as well as making reference to the mathematics, because it is crucial that you sort of understand. So please take an opportunity to go back and look through the slides we've posted. Sorry, actually, oh gosh, actually, I realized that this. Yeah, no. This slide is a Google slide that's posted in the directory. Or if it isn't, sorry, I better move it there. I'm realizing now I'm not sure actually whether this version I'm talking from is, but anyway. But it will be there shortly. So the binary cross entropy, what is that? Well, I hope as physicists you may have come across entropy already, but essentially what you're trying to do is to create a number which represents the number of ways in which the system can be arranged. Now, it's binary because we are trying to consider a simple binary classification situation. In the slides, I borrowed some graphics, as you'll see, attributed to someone who does a very good job, I think, of explaining these things. So I've repeated his work and give you a link to the original stuff. But you could talk about events being red or green, say, or in the case of our workshop, we're talking about narrow pulses versus wider pulses. And what you're trying to do is to, as I say, just characterize the sort of the uncertainty associated with a given distribution. And what's interesting is we're going to do it in what's called cross entropy, because we have a system that is characterized by some given distribution Q, and where the possibilities are given essentially by Y, which in the case of color would be just simply Y is either color red or color green, or the Y in case of our example is just narrow pulse versus wide pulse. So again, we've tried to limit it just to a binary situation. But why we talk about binary cross entropy is because we're actually going to use two probability distributions. There is the underlying probability distribution, which in this notation here is given by Q. But we are actually going to have our own probability or proposed distribution. Let's use the P, proposed distribution P of Y, which is what our net is being trained. We're attempting to train the net, and P of Y is its probability, its best guess at what the probability distribution is. So it's a cross entropy because we're trying to compare, if you like, what the underlying behavior is with what our net is being optimized on. So so the next set of slides really go deep into trying to give you a sort of strong sense of how binary cross entropy works. I think it's important because this is that we are going to create a loss function based on this statistical test. Now that the idea of a loss function, why do we talk about loss functions? You could talk about loss functions, or you could talk about how well we're doing, a goodness function. It turns out that by convention, we tend to talk about loss, meaning the larger this number gets, the worse we are doing in terms of this binary cross entropy, i.e., we're doing a bad job of our probability distribution that the net represents is just not characterizing the underlying distribution very well. That loss function will improve the better and better we get at estimating what the probability or understanding the way the probability is behaving. And the way that the way we can only do what we're doing in terms of our probability, as it were, is we're just simply taking the pulse shape that we have, and we're trying to say, do we predict that pulse is a single pulse, or is it a two pulses smushed together? So that is the task. We're trying to do our best with the time trace in order to do this. So as I say, slides will be available to you, but I try to pick out as much as I can from Daniel Godet's extensive work, ideas that I think should really help you understand or get a good idea of why binary cross entropy in the case of this two classification model that we're doing is a good thing to do. And I've mixed some of his graphics with the standard formulae because I think his graphics do a great job of helping one understand that. But we are not, we don't have the time to go through that. I just wanted to highlight this as this is the loss function that turns out to be very effective at when we calculate it based on how well classification of our net is doing with training data. We're trying to minimize the loss, if you like, or maximize the goodness, the performance, but we tend to talk about minimizing loss as a thing. Now, the other thing I want you to go away and look at is convolution. So I prepared some slides on this, again, with the help of Austin Weitges, and the people who helped me with this are listed at the front. But a convolution is mathematically looks like this, which I know tends to put one right off, unless you happen to think like this, which is great. You play with this stuff enough, and that kind of mathematical representation begins to become pretty obvious. But let's show you graphically what this means. Is we're basically taking the red function, the function that's moving across the screen in the upper graph, and we're moving it across our input function, which is the Gaussian, and the output is shown in the lower window. Now, why is that useful? Well, because it turns out that a number of features are being extracted by this convolution process. So in the case of the data you're going to be working at, we have 700 samples running from early time to late time. And your network actually includes exactly what's being shown here, a convolution that is being run across the data. And the key is that the shape of the convolution function, as represented by this moving red filter, that is up to the net to attempt to optimize. And it doesn't just optimize it once. We actually give it the option of 8 in the first convolutional layer. We give it eight separate filters that it can play with. And then we give it another 16 separate filters it can play with. And what's actually happening during the training is it's trying with some of those filters. Some will be a disaster and it'll just ignore them. But a few of those filters, it will happen to converge on shapes that are giving you maximum information extraction concerning the pulse shapes, the S2 pulse shapes. And that's what we're sort of relying on happening. That's the convolutional neural net part of it. At the same time, we also have a deep or potentially deep net also acting on the outputs from these convolutional layers. And it's some combination of these two that we are relying on to help create a net which has a smaller loss, binary, as measured by this sort of statistical binary cross entropy measure. Okay, so I've taken a few snapshots there, but we're getting to the top of the hour. I've been talking for 48 minutes, 50 minutes now. I hope those slides in all their glorious detail will be useful to you. Now, Sean will be talking about this, but this diagrammatically is trying to show you the flow. We basically got the S2 pulse, 700 separate samples, some sort of Gaussian-like shape, but we don't prejudge that. Then we're going to apply convolutional gates or filters, sorry, convolutional filters to the data. Then we're going to take all of that output, flatten it, and put it into a dense layer that contains one or more intermediate layers. And that's the system that will then all funnel into a single output. And the single output is then going to basically say red or green, or in this case, narrow pulse or wide pulse. Narrow pulse is considered to be truth, 1, and wide pulse is considered to be truth of 0. So you'll be following, in the Google Drive, you just Indico will give you the link directly into the folder. This is the LZ dark matter pulse shape classifier example. And I think I've covered most of what in these summary slides was going to be thing. But I did want to mention a couple of things. With the network itself, the network is free to try to pick, as it were, the nature of the strength of the function that couples each of these layers together in terms of both what's called a weighting function, but also a bias, which, if you like, is a fixed offset. So those parameters, as well as the convolutional filters that are being changed, it's the weights and biases that are also being in the deep layer deep layers that are also being thing. And then we have not. You have to put in as a suggestion for an activation function. Now you should mess around with this offline, but it turns out that if you just put a linear activation function, and it's extraordinary, your net really behaves pretty badly. And it turns out this nonlinear sort of function here, which is sort of asymmetric, it's basically 0 transmission for inputs that are less than 0, say, but for positive ones so it's a semi-linear function, otherwise known as the ReLU. You get much better behavior in nets which are coupled by, for instance, an activation function of a ReLU type than you do of a pure sort of linear, which was just minus to positive straight line. This is an area which you should try to take time to see whether you do it. Now, the last thing we need to cover is the output. We're trying to classify between two possible outputs, narrow pulse, wide pulse. It is typical to use, and again, ultimately, once you get something that's working, you should go back and see how introducing different functions work. But the sigmoid function is one that is usually a great first guess for how to apply an output function, which, when all of these signals are being combined through the weights and biases into the final output node, how does the output node actually combine them through some classification function? A sigmoid classification function is a good one to choose. Okay, so this is what we're going to do. We're going to do a binary classification of single scatter versus multi-scatter, single Gaussian. It's not, sorry, I shouldn't keep calling it Gaussian because it's not exactly a Gaussian. It looks Gaussian-like. But this sort of bump shape or double, or is your bump hiding actually double bumps, two bumps? So this is what we're asking the net to do, and we're going to train it using data that is identified as single bump versus double bump for the classifier, but that will then run it over data where the net doesn't know whether it's a single or a double, and we're going to be looking at the what its classification output is. Okay, so here, and I hope this one's relatively easy for you to do by eye, we have example on the right of a single scatter, single energy deposition. One on the left has two bumps hidden together, and because they're far enough apart, you can actually see that the thing is getting wider. So that one you can do by eye, but you'll see if you actually dig down and start looking at what we're giving the net to do, many of those events are narrower sorry, the two bumps are so close to one another that they almost look like a single bump. And the question is, how well can it do on those? How well does it distinguish those bumps? And Sean and I, we want to make sure you understand. Unlike conventional visual, systems where we're often doing 2D data, or as some of the workshop examples we're using 3D data. This is just a 1D. It's a time series. We're still using convolutions, but these are 1D convolutions rather than two-dimensional. It's more common in sort of visual systems, but they computationally they're very fast, and this is a great system to explore the behavior. Okay, so I think I think Sean is probably going to be talking about this, but again, I wanted to put these slides up because if you're very new to the field, you may still not be comfortable on this, but there are two acronyms you've got to get solid with. The first is ROC and the other one is AUC. So the ROC curve is an opportunity for telling how well our network is doing. And it's basically a comparison of what's called the true positive rate with the false positive rate, which means essentially how often for a given ensemble of events, as we sort of vary our discriminator, whatever it is that we're using to sort of, if the output is less than the discriminator, then it's single, narrow pulse, and if the discriminator from the net is, if the value that comes out is above a certain threshold, then it's a double multiple scatter event. As we vary that actual threshold around, you get a certain number of true positive events, i.e. correct, we know we've correctly identified something, versus falsely positive, i.e. something that was incorrectly identified. Now, if your network is completely random, you get the dotted line. So as you vary your discriminant, what happens is you get as many truths as you get false positive identifiers. That's that's just no good, because you really can't use the output. What you want is a curve that rises rapidly, so the true positive identification is rapidly heading towards 100% or 1, and while the false positive rate is staying close to 0. That's what we want. Now, the term ROC actually is receiver operating characteristic. Why the hell would we use a term like that? It turns out it comes from the Second World War, when early radar were being tested. And TPR that we use now is basically the successful identification of real objects with the radar. And FPR is false alarms or ghosts or noise, where we say there's an object, but in reality there is not an object. So that's your false positive rate. So the receiver operating characteristic, it literally meant receiver as in radio receiver operating characteristic. And we still use this term ROC, today for this kind of work. And then you may intuitively understand already that the area under this curve, if you're in the 50-50, no performance, bad situation, the dotted line, then you've got an area of about 0.5 under that line, that would correspond to the system doing no use. True positive rate is the same as the false positive rate at all discriminant values. What you want is a AUC, an area under the curve, which is substantially larger than 0.5, close to 1. That would imply your TPR is going up very dramatically, but your false positive rate, FPR, is still close to 0. That's a performant network for a given population. So that's AUC, area under curve. You want to be close to 1. So this is another way of characterizing performance. Okay, so that's it. You may want to flip back to this slide. As I say, I'll make sure it's in the folder accessible directly, but you may want to flip back to this slide, because but Sean, in the notebook as well, I think Sean's made sure this is called out as well. It just tells you a bit about the way the data is done. Okay, and then in this notebook is details of how to contact Sean, myself, some of my other colleagues in the group, if you want any advice about about what you've seen. Anyway, thanks very much. Okay, I should stop there, and we're going to need a 5-minute or certainly a few-minute break before we go into Sean. Sorry, this is the problem of me chairing myself. I've overrun. Anyway, okay. Yeah. if there are any questions while everybody's taking a break, I'm happy to address those questions. Otherwise, Sean, do you think what in 3 minutes, say at 10 past, or do you want 8 minutes? Should we say quarter past to start the workbook?
3 minutes is fine, but I think there was a question from Dylan. He had his hand
Ah,
up, it seems.
okay. I'm not seeing it though. I don't know who's typed it. Are we?
Oh, he had
I'm
his
gonna.
hand up. The hand is down now, so maybe there's no
Okay.
more question.
Okay. No, maybe that was just a. Okay. Anyway, we're going to just break for a few minutes so people can go restroom, grab a coffee or what have you, and then Sean will. Uh, oh, here we go. Oh, it was a clap. Sorry, somebody was clapping. Thank you. Yeah, no, yeah, well, we used to say smoke them if you got them, but we don't do that now. So no, let's reconvene and the workbook, and I'll use the next 3 minutes to make sure the slides are accessible in the Google folder as well. Yes, so the videos are going to be posted in Indigo. Um, they do need to be edited. Um, so I I will be probably at the beginning of next week, I think, that we actually get to have them posted directly. But rest assured, they will be posted. It will happen next week. Exactly the timeline I'm not clear about, but we'll break them up into the each of the lectures and each of the work sessions will both be videoed, have both been videoed, will be broken up accordingly, and will be made available. And just keep the Indico address, um, um, and you'll be able to see them posted there. We'll make sure that if you have the Google Drive address, then at the root level of the Google Drive, there'll be a README that includes the link to the Indigo as well, so that you'll be able to see very easily how to get the videos. And as I said, I've moved. Apologies, I didn't have the live version of the slides in the Google folder as I was talking, but they are now there as a Google slide document. There are a fair number of support slides, um, so you'll just have to look at I indicated by hiding many of the slides that I didn't talk about. Also, off the end of the presentation, there are again slides which will help you for context. I basically put information that I thought, if you're trying to get up to speed, depending on your level of existing familiarity. But I hope you see quite clearly from the workbook example that Sean's going to be doing now that we're trying to make this particular example as I would recommend anybody who's newish to machine learning. This is a great example because we've simplified it to really make sure you understand every step. So I hope it won't seem like a black box to you. This is important. We don't encourage, we're able as scientists, as analysts, as physicists to actually understand every step that's going on in these workbooks. Sean, I should hand over to you at this point, please.
Yep. Let me share my screen. And everybody should have copied everything from the CFPU shared drive to their own local Google Drive. Okay, wonderful. Can everybody see my screen? And please feel free to type things in the Q&A or the chat box if you
I'll
need
I'll
if you need to.
I'll keep an
Yes.
eye on the boxes to make sure we can see
Okay.
and can see your screen clearly. That's good.
All right, wonderful. So this is the Colab workbook that we've set up for the pulse shape classification in LZ using simulated pulses. Um, Simulated because in particle physics we quite often work with simulation first, just to get a handle on what we're doing and to perform blinded analyses. Um, but the pulses you are using today are things that we do actual research with. These are not toy pulses we've contrived specifically for this workshop. So I hope you'll get, hope you'll think you're, I hope you think you will get something very useful out of this today. And at the top, there are some links. There's the Indigo link, there's the Google Drive link, but then there's the CFPU link, which is the Center for the Fundamental Physics of the Universe within the physics department at Brown, which is putting this workshop on. The authors, myself, and the whole team. And the last two links are to LZ, which I encourage you to go to because LZ is an important experiment when it comes to dark matter because dark matter is one of the biggest unsolved problems in physics currently. So please go there, please explore the physics that's going on there and the technology. It's particle physics experiments are very much a tour de force in not only physics analysis, but as well as technology. So if you're interested in the engineering side, please absolutely go look this up. And I encourage you to try and at least read or skim through the entire notebook before starting, just so you know what's going to come up, so you won't have any surprises, so you'll be primed and ready. But other than that, we can get started. I should say first we're using TensorFlow Keras here, which is a free and open source software library developed by Google. Um, the other very popular library is PyTorch, which some of the other workshops may have used, or some of the other modules may have used, but we're not doing that today. But you can if you like. They're sufficiently convergent in syntax that transitioning between one and the other is not shouldn't be an issue. But okay, let's go ahead and set up our workbook. So here and in other places, you may find that uh, using different processors is beneficial or not. But if you want to change, if you look up here in the upper right, it'll tell you what type of processor you're using. So there's TPU, which is a tensor processing unit, which was developed by Google to perform efficient tensor operations. So a simple example of that would be like matrix multiplication. Colab, I think, defaults to that. But if you want to change it, you can just go up here to runtime and then change runtime. You can change it from CPU or TPU to CPU or the free GPU that you have. The GPU, the resources that are provided in the free Colab are limited, but they should be sufficient to run this workbook. Um, you can use either one of them. I have mine currently set to GPU, but for the purposes of today, the run times will not be changed so much that you won't be able to finish this workbook outside of this time limit. Uh, so that's all for setup. Does anybody have any questions on the setup or anything so far? Anything at all? Even the previous talk by Professor Gateskill. Any questions at all? Could be about the physics, could be about the machine learning, could be about, you know, dark matter in general.
I'll give you a shout if anything appears. Nothing there
Right,
at the moment.
right on. Okay, so just to reiterate, the goal of this module is to discriminate pulses or time traces of events produced by particles scattering within the Lux-Zeppelin volume. So pulses that will scatter once or multiple times, rather twice, um, and get detected within the LZ experiment. You'll use a neural network, perhaps a convolutional neural network, to try and complete this task. And you will try the best you can to optimize the performance of your neural network model to discriminate between these single and multi-scatter pulses. And by the end, you should be able to produce some plots that tell you how well your model has performed at this discrimination, or rather, I should say, how well your model has performed at the performing this binary classification task. And so, as mentioned before, since you're doing binary classification, you will uh, produce a plot called the receiver operating characteristic curve, which plots the true positive rate versus the false positive rate. And this will give you your performance metric. Uh, Namely, from this, you can acquire something called the AUC, the area under the curve. And as was said in the talk, if you have an AUC of zero point 0.5, well, that's no better than flipping a fair coin to decide between your binary classification. So you want to get this AUC as close to 1 as possible for both the training data and the data with which you will test your model on. And I'll explain why later. Well, actually, I'll explain why now, so, since it says here. Um, if, for example, your AUC or your whatever performance metric you have in any machine learning model, if it performs better on the set that you're training with and doesn't perform so well in the test set, well, that means it's overfitting. What does that mean? Overfit model means it's memorizing the features of the training set and not performing well on data that it has never seen before, that has never been trained with. In other words, it's stereotyping based on the training set. And so it doesn't quite understand data that it has never encountered before. So you want to mitigate this. And one metric of overfitting is if the look on the ROC curve and the AUC of the the AUC of the test set is worse than the training set. So that's one thing to look out for. That is probably the thing to look out for in your performance metric, to make sure that you know your neural network model isn't memorizing just the training set. So what are you going to do for this exercise? Well, down below, you're going to see a bunch of question marks in the model. I've written a skeleton model for you, and you're going to have to fill in the question marks for what you think the most appropriate things are to fill in. Now, as you heard in the talk, uh, there are specific things that you might want to consider. So hopefully you remember those. Maybe you can go and pull open the slides and see what those are. But at the end of the day, it is up to you to optimize your model to get the best performance. And there are some ways to do that, and I'll explain them. But for now, why don't we just go on with the exercise? So hopefully you guys know where the shared folder is. Hopefully this is not your first go around in this workshop, and you've made a copy of the exercise material in your own Google Drive. And when you do, when you copy the files to your Google Drive, uh, they will be named something with, copy of file dot whatever. That's not an issue for today. You can leave those file names, i.e. copy of as is, because I've written this this exercise such that, as you can see down here, that this is already taken into account here. So in principle, you should not have to change any file names or anything like that. So please go ahead and you don't have to, by the way, you don't have to do what I'm doing at my own pace. You can do it at your own pace if you like, or slower, whatever you're comfortable with. But, you should first import all the appropriate libraries and then mount the Google Drive. This may take, okay, it doesn't. And then load the file. The file loading, because it's quite large, it's order of 100,000 events, about a gig in size. It may take up to a minute to load, but fear not, it will load. If anybody has any comments or questions about the code or anything we've said, you noticed a bug or you want some clarifications, please raise your hand or email us or whatever. Uh, okay, that's an issue with me, but that's okay. That shouldn't happen to you. It's because I reloaded the thing earlier. But afterwards, you can display the data, and this display needs a little bit of explanation. So the column labeled DS data, these are the pulses. And so the pulses are 700 samples long, each one sample representing every 10 nanoseconds. And you see a bunch of zeros here, but I promise you they are not populated with zeros, and I will show you this below. The UL values tell you the properties of the pulse, the simulated pulses. You don't really need to know what they mean, except for perhaps this guy here. The truth values are to distinguish between single scatters and multi-scatters. So 0 i.e. false, is a multi-scatter, and 1, i.e. true, the positive class, is a single scatter. So you'll notice in the false class, the multi-scatter, you have this number 950. This is a number in nanoseconds, and it tells you the time difference between multi-scatters. So you'll notice if it's a single scatter, it does not have this. But the key takeaway is you have two classes, multi-scatter and single scatter, that have been labeled with 1 or 0, the typical true or false. So because we have this labeling, we have this truth value, this is going to be a supervised learning task. So we can go down and visualize a couple of the pulses here. So the first one is a multi-scatter pulse. As you can see, it's quite wide compared to the single scatter pulse. And just because of the way we've contrived the data, of course, you have these zero values at the tail here, which is what these zero values in the in these columns are. Um, but you can see there is a definite pulse here, a definite difference between the pulses. The multi-scatter pulse is in fact wider because it has these two scatters on top of each other, as compared to the single scatter, which is very obviously much more narrow. Now, this multi-scatter pulse has a very high time difference between the scatters, i.e. delta mu has, for example, it's probably one of these, the 950 nanosecond delta mu's. But for lower values like 100, the multi-scatter pulse is going to start to appear like a single scatter pulse. Uh, and that may cause some issues for classification, or it may not. If it does, it's your job to figure out how to get around this problem or work through this problem or train the model in such a way that it can understand this region of parameter space. Okay, so what's going to happen here? This is just another visualization of the pulses. So you have the positive class pulse, i.e. truth value equal to 1 for a single scatter, a truth value equal to 0 for a multi-scatter, as you can see again, this is a wide pulse, a wider pulse, and then another value of a single scatter. And please notice the time is in nanoseconds here. And the y-axis, we should say, is the amplitude of the S2 pulses. Remember, we're working only with the S2 pulses here. And the S2 pulse amplitude is PhD per 10 nanoseconds. So photons detected per 10 nanoseconds. So let me scroll up. What these pulse trains are just the values of the pulse height, the S2 pulse height. And these are going to be labeled by either 1 or 0 to denote single or multi-scatter. And hopefully your neural network will be able to tell the difference based just on that. Yes, okay. Anything so far? I don't see anything. Okay, where am I? Right, okay, good. Okay, so as I said, there are 100,000 events total, but the free Colab instance typo here, I'll fix that later, may not handle that very well. You may have to upgrade to Colab Plus or whatever it's called to be able to handle that. But it should work on 50,000 events and it should perform the training just fine. You can tweak the number of events that you want to use here in the end events variable. Uh, I suggest you actually do play around with this on your own time because uh, you'll see with fewer or more events that the training will proceed differently. Your training performance will be better or worse depending on the number of events you have. And it's always a good idea to have as much statistics as you can so the neural network can understand any complex patterns that you have in there. So again, I encourage you to, you know, on your own time, over coffee or dinner, but when you're about to go to sleep, you want to do something, let's say decrease this by an order of magnitude or two, just to see what happens to the training. Or maybe increase it by, go up to the full 100,000 events or, three-quarters of that, and then just compare the training. I promise you, you will notice differences, both in the training speed and the training performance. Okay, now down here, I have shuffled the events. And why might I have shuffled the events here? I've randomly shuffled the events. Why may I have done that? Does anybody want to throw out an answer? I'll poll the audience here. Does anybody have any idea? Just shout it out, open your mic, or type it in the chat. Anything at all? Any guesses? Why the data? It's good to randomly shuffle the data before training here. Raised Dennis. You can
Uh,
shout it out or you can type it in the chat.
okay, can you hear me?
Yes, I can hear
Yeah.
you.
Fine. It is usually we shuffle data because you can have your data. I mean, if you do, for example, binary classification, you can have first half of your data set with zeros, second with ones, and if you do not shuffle data, you can have a biased output after training your model.
Exactly right. Exactly right. So what Dennis was saying was that if we don't shuffle the data, the first half will be all zeros. And then the neural network may just, for a while, see only zeros and it'll just start learning what those false classes look like. And if it starts doing that for the entire first half of the data set and then looks at the one, and then it may get confused. It may output something that's biased toward perhaps the first half of the data set. We want to avoid that. We want to give it sort of a random sampling of events to avoid this bias here. That's why we shuffle it. It's a good answer, Dennis. Now, I'll talk about a little bit of feature selection. This isn't such an issue here, at least not explicitly. Usually in machine learning, you want to pick out some features, i.e., things that will help distinguish classes between each other. Now, in convolutional neural networks, this is sort of done for you in the convolutional layer. When you train the neural networks, if you use convolutional layers, the weights and biases in them will be trained such that it will sort of automatically pick out these features. But if you're not doing that and you want to classify, say, in doing binary classification between, I don't know, dogs and cats, for example, uh, one feature you may decide to include in the neural network training as a training feature is, for example, the snout length of the dog and the cat. Dogs, unless it's like a pit bull or something, dogs have generally a longer snout, and that is one feature you could use for that. But that's an example of a feature. Features may be inherent to the data. You may know them, or you may have to perform some sort of feature engineering where you develop your own features that represent the data better than you already have if your training is not proceeding as you'd like. So what you want to train in the neural network are the weights and biases, and in convolutional layers, if you use them, are in the filters. Uh, the next thing you should know, the key term is the hyperparameter. The hyperparameters are non-trainable parameters, things that you can select, like the number of neurons, the number of layers, the number of filters in the convolutional layer, the filter or kernel sizes, et cetera, et cetera. So these hyperparameters are things that can be chosen or optimized, but are not trainable. The things that you are training are the weights and the biases here. Uh, and so let's move on down here. And so we're just gonna pick out the training set. We're just gonna select out the column with the pulses, and then the targets or the labels will be the truth values, the ones or zeros that put things into classes, these binary classes. So remember, the positive class is the single scatter, and the okay, you don't need to worry about that. I don't, or you don't. And the negative class or the false class are the multi-scatters. Okay. And so we want to create the training set because TensorFlow kind of likes NumPy arrays. We can throw it into a NumPy array here, and then we can reshape it. These are just technical details. You can ask me offline about them later if you like. Um, But then we use this function called train test split. And train test split is a function from the scikit-learn library, which is also a must-have for machine learning. So if you go up and look at the imports, you will see I've imported, or hopefully I've imported scikit-learn for you. And it provides this function called train test split. So you give it the training data, and you give it the targets, and you give it a split size. So it'll randomly take 20. So I've set it to 0.2. So it'll randomly take 20% of the data and hold out as a test set, so you can test your neural network later. And I've set the random state to 42 because, of course, 42 is the answer to the universe. Hopefully, some of you get that joke. And then here you can just print out the shapes. The shapes are given by the batch size and the pulse shape. So the batch size is just the number of pulses that you have here. So you have what, 40,000 pulses here in your test set. And remember, because I'm only using 50,000 here, you can change that as you like. 700 because there's 700 time samples in the pulse train, and then 1 because there's the pulse arrays have just 1 pulse per array. And then the target shape is just you have 40,000 targets, so 40,000 ones or zeros. Okay, so now the model. The model is this is sort of the heart of the exercise. This is where you're going to do most of the work. Um, and the model is defined in a function that I wrote called build a model. And it's what creates the neural network model. And then your task is to select the appropriate layers and hyperparameters of the layers, i.e., the parameters that are not to be trained, like the number of layers, the number of neurons, the number of filters, the kernel sizes, etc. That's your task. And so I've listed a number of things here that you should do or you should look at. And so if you decide to use convolutional layers, technically you don't have to, but I've written it such that it will be easy for you to do. And convolutional neural networks are often used to analyze time series data, long time series data. There are other ways to analyze time series data, for example, recurrent neural networks, but CNNs can be one of the ways you do them. And one of the things we have experimented with here. There are nice properties about CNNs involving translation invariance and stuff like that. Um, but suffice to say, CNNs are very good at not only image classification, but also working with time series data. So if you decide to use convolutional layers in your neural network, um, what might you decide how might you decide to parameterize them? So for images, in two-dimensional convolutional neural networks, remember we're working with one-dimensional here, but just to give you some motivation, uh, size kernel sizes of 3 or 5 are often used for image recognition. But for our pulses in a 1D CNN, does that make sense? If you have a 700 sample long pulse, do these small sizes make any sense? Can features be accurately captured in such a long pulse train? I don't know. That's up to you to find out. If you decide to if you do decide to use convolutional layers, you have to think about the number of filters and, of course, the kernel size, as I just said. So this is something that can be optimized, and I will tell you the sort of more technical way to do it. You can type in different numbers by hand and plug and play, but when you go home and look at this later, you'll see that there's a more efficient way of doing this. For the dense layers, there are things called which come usually in a convolutional neural network, which these dense layers technically can come anywhere, but oftentimes they come after the convolutional layers. You have to tune the number of hidden layers, which for this purpose I've labeled end hidden. Hidden layers they technically mean the layers between the input and output, so you can technically have the convolutional layers as hidden layers. But just for this exercise, I've labeled the dense layers as end hidden, and you have to figure out how many of those you want and the number of neurons associated with them. So dense layers means all neurons are connected to all of the ones in all the other layers. Whereas in convolutional layers, one neuron is only connected to a subset of the preceding layers. So convolutional layers are different than dense layers in that way. But in the model below, you'll have both dense and convolutional layers, and you'll have to decide the number of them to have. And technically, you don't need to have any. You can just have something that completely passes through from the input to the output, but it's not going to be very useful. And further, you're going to have to choose the learning rate. The learning rate will modify how fast the optimization, i.e., e.g. gradient descent, will optimize the parameters at. And a reasonable starting value for this exercise may be 1e minus 3, which you can just type in like that to the neural network model. You can play around and tune this, make it higher or lower. But if you've read the primer slides on the beginning, too low of a learning rate will cause the neural network to not converge fast enough. Too high may cause the neural network sort of bounce around the local or rather global minimum and never settle down. So you sort of have to play around and find out what the best one is. You have to figure out activation functions. The activation functions add nonlinearities into the neural network model, and sort of so you have some for the dense layer or for the hidden layers, and you have one for the output layer. And so these will be different. Professor Gaskell sort of hinted at what they may be in his talk. So if you want to go out and see them, please go and open that talk again, and the answers may stare you right in the face. Optimizers, I've sort of defaulted to stochastic gradient descent here. Stochastic just means random. It'll just randomly pick out a training instance rather than using the whole batch at the same time. But you don't have to use that if you don't want. You can go to reference number 3 and look at the available optimizers. And finally, you're going to have to pick out the loss function from this reference number 4. And the loss function, well, please note that we are doing binary classification. The loss function you may want to use has already been named, so technically you don't have to use that. You can experiment with other things, but please do remember we are doing binary classification. Hint, 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 hint. So in reference 4, you may want to look under probabilistic losses to see if there's an appropriate loss function there. And so I've sort of given away part of the answer here. The output activation function is perhaps the sigmoid activation function, but why might we use that? A figure was shown of the sigmoid activation function. It saturates between at 2 values. Please go and look at that and ask yourself why we may want to use that. And the other only thing that has been hard coded for you is the input shape. The input shape is the shape of the pulses that we have in the data. Don't change that. That should be fine. And the last thing I will say before I set you on your merry way is how to optimize or tweak the model hyperparameters so you don't have to keep typing in things by hand. So there are 2 things called grid search CV and random search CV in scikit-learn. And what these do respectively is, well, if you have you can select a range of hyperparameters that you want your neural network to look through and try and optimize the network based on these choices. So that's what grid search CV will do. You just give it for lack of a better word, a grid of different hyperparameters, and it will step through them and look how well the model is performing based on combinations of those parameters. If that set is too large, you can use the randomized search CV, which will randomly select parameters from that basket and search that. And there's something else called Keras Tuner, which you can also use, but I won't get into. None of these are here today. These are things that you should go home and play with by yourself because it takes a little bit of time to set up and search through. Okay, thank you very much. But for that, that is all I want to say. All of the things that you need are in these links here, especially the first one well, maybe references 2, 3, and 4 are probably your most important ones right now. So you should click those and see what you get there. And then based on the answers there, you can type in something here. For example, if you want to use the ReLU activation function, you can just type in ReLU here. And I just want to note that this model is called a sequential model, where just the layers come in sequence, one after the other ones. If you want more flexibility to your model, where you don't want that, or you want, let's say, you want to chain two sequential models together, for example, there's something called a functional model. We won't get into that today, but it's just for you to know that there are ways of building flexible, more complex models, as many models these days are, like large language models. So now I would encourage you to play around here. So you have the number of hidden layers in the dense network, which modifies this part of the code right here. Number of dense layers will n hidden will modify the number of dense layers in your neural network, and the number of neurons will say how many neurons are in each. The activation here, you can use this, or you can use another one that you find. It's fine. Depends on the performance of your model. And of course, the learning rate. You can set it here. Um, the Yeah, sorry, there's a question somewhere.
No, that was my
I
bell.
see. Okay. So here are convolutional layers. I've put two in here. You can take them out, or you can add more. Completely up to you if you want to, depending on how you think your model will perform, or based on your model performance, you can change this as well. So the number of filters which output these so-called feature maps, and the kernel size here. And so Professor Gateskill sort of hinted at, you know, numbers that you might put in for the number of filters. And above, I had some starting points that you can start here, which may or may not be good for this problem. So I said maybe an image classification, they use 3. Um, you can try that. It's up to you, but it doesn't have to be. But all you need to do for this is just type in that. Don't worry about what this means for now. Um, Down here is the output. So this is what's going to give you your answer. So once a model is trained, once you pass the test set through the trained model, this is what's going to give you sort of your let's say answer, for lack of a better word. It's got one neuron here because we're just doing binary classification. We wanted to give us just one single class guess, or rather a class probability guess. And I'll explain that down there. But the output activation should be something that you've heard before in this module. Um, so hopefully you were paying attention. The loss was already a good guess that the loss was already mentioned before. Um, and the metric is not something that's involved in learning here. It's just a way to monitor your performance during training. So for this, you might want to use the accuracy metric. I'll just type that in there for you. Okay. Everything here should also be saved into your local drive. So once you run this exercise, there should be plots in your own local Google Drive. Um, that's sort of an answer there. I won't do this right now. So right now, I'm just going to let you, if you haven't already started, I'll open the gates and let you run wild with this for a few minutes, let's say 5 minutes, and then I will go on. And please, any questions, raise your hand or type it in the Q&A, and anything at all. Please let me know if you're confused on anything. So just a note, when you go to this website, and you want to, for example, input the activation function or the loss, for our purposes, for what we're doing today, you can just use the string that it gives here. So for example, the ReLU you can just put this ReLU string in here. Or for the losses, you can do the same as well. This is just so you don't get confused on what to type in. Uh, you can just For example, you can just put for the loss, you can just put in a string, put in this string. There are other things, there are other ways to do this. Um, but I've wanted to make it such that it's very easy to just type in a string here. So don't get confused. Just go to the website, look at the name, the string name, then or rather the name string, and just type that in.
Sean, apologies if you answered this already, but there is a question in the Q&A.
Oh, I'm sorry, I didn't see.
Yeah, sorry, I missed that. From Toby, can you explain the approach to determining the number of filters in the kernel size? What features of the pulse data can help us determine this?
Yeah, so for example, one thing that was strongly hinted at earlier was like the pulse width that can help us determine this, and the sort of the Gaussian shape can help us determine this. Um, the number of filters and the kernel size are things that you can optimize via by the methods that I mentioned above, but you want to use perhaps some sort of physically sensible kernel sizes if you decide to use convolutional layers. So for example, 3 and 5 here are good for a lot of image recognition problems, but we're not doing image recognition problems. And we have a very long pulse train here. So you might think of using something a little bit longer to capture maybe more of this the features of the pulse, like the width or other things that are sort of intrinsic in these pulses here. But like I said, you should go home today and play with these optimization methods and see what parameters that you get for this optimization. It may not be 3 and 5, it may not be 500, and maybe something in between. It sort of depends on the problem and the data at hand. So these are things that you can optimize and you can give it sort of sensible guess, or if you don't want to use that, you can sort of give sensible guesses based on the data that you have. But but again, there are methods to help you with this optimization here and choosing these hyperparameters. Yeah, so as I said before, those parameters are sort of just guesses that may or may not work, depending. You can test it out yourself and see. You can train this thing multiple times. Although if you train it multiple times, you may have to restart the session just in case there's sort of any lingering memory in the training. But you can test this multiple times. It doesn't take very long to train. Um, don't necessarily copy what I have. They aren't necessarily the best things to have. These are just sort of, examples, starting examples. Um, but here, down here, you'll see a sort of flow chart of the model. So you have an output, or sorry, you have an input, and then output here. You have your convolutional layers. You have a flattened layer. Don't worry about that right now. And then you have these dense layers that sort of perform more learning for you here. And then after that, this sort of the critical part here is tr the training the model. Now, there's something called a validation split. Um, you can really there are sort of three data sets you have. You have the training set, which you train your model on. You have the test set, which you've tested your model on, and then you have the validation set, or which you can sort of reserve for yourself on your disk, or you can have uh, set this validation split here in your training, which is down here. And what this means is that on each epoch, and epoch means one pass of the data, it will hold out 20% of that training set to evaluate itself on.
Stuff on.
Yeah, so I'm getting a little bit of feedback here. Somebody has their mic open. Hopefully not. Maybe that's just me. Anyways, so for each epoch, it calculates its loss and then the accuracy metric, which doesn't have to do with the training, but it's a good measure of progress. And then the validation loss. So it holds out 20%, and then from the training, and then it evaluates itself on this. And sort of the validation loss is what you want to look at during training to see how well the training is performing. If the loss is improving in whatever way it should improve, but the validation loss is not, there's something perhaps wrong with this. Is perhaps there's overfitting, whereas in the training it's memorizing features, but in the held out set it's not performing very well. So it's good. It's not required to have a validation set here, but it's good general practice to do so. You can set the number of epochs. This should be X train. Oops, X train X and Y train. But actually, this doesn't matter so much. But what you want to do is set the number of epochs. So the number of passes of the data that it takes to look at the number of passes of the data that it takes to look at that it takes to train the data. So I've set it to 5 here. That may be too short. In fact, it is too short. You maybe set it to at least 10 epochs, perhaps 20. I tried it with 20 last night on the TPU, and that took about 30 seconds per epoch on the TPU. This about 5 seconds per epoch was on the GPU. So definitely a difference, but whatever you choose, it should be fine. So when you train this, you have something called callbacks. Here, our callbacks are tell us how to stop the training. So one callback is called early stopping, and what that means is if it doesn't find any improvement after 5 epochs, it will stop the training. Why is this? Because if you go down here to the learning curves, the green is the validation loss, and the blue is the loss. So if your loss keeps improving, i.e., the loss keeps going down, but the validation loss doesn't improve, well, it means it's improving on the test set, but not the validation set, i.e., it starts to overfit. So you want to stop that overfitting before it gets too wild. That's why you have early stopping. There's another thing called reduce learning rate on plateau. This is the callback where it looks at the validation loss, and if it doesn't see any improvement after 5 epochs, then it will reduce the learning rate. What this does, reducing the learning rate will help the model find the minimum a little bit better, find the optimal solution a little bit better if it doesn't see any improvement. This I didn't add this in here. I have this commented out. If you want to uncomment it and include this callback here, you can. And you can play with these parameters too, if you like. But I've only have the early stopping callback. You can change the parameters of this if you like. But this is all completely up to you to determine how well your model performs. And so the red and the orange curves are the accuracy. Again, a good metric to look at, but not involved in the training. It's the loss function that's involved in the training because you have to take derivatives of it, or the gradient of it. So if this is going down, it's good. I only have it at 5 epochs, so it's not, you can't see it going down very well. And it already sort of started out in a reasonable state where the accuracy is high and the loss is relatively low, fairly low, but although, of course, you can see improvement. This doesn't always happen. Sometimes you have to play around with your model or better yet, get more data and play around with your model to improve the performance. But these curves are what you want to look. This is called the training history, and it's a function of the epoch. So down here, I have the training history saved. You can save it and produce this plot on your own later. But this should be saved into your own Google Drive here. I have these functions to plot the ROC curve, as Professor Gaitskell talked about earlier. And then down here, you can evaluate the model's performance on the train and the test sample. And so when you do that, you can produce a rock curve that looks something like this. Remember, I only trained it for 5 epochs, so it looks a little bit looks the sort of elbow here looks a little bit weird. But you can go down here to this example rock curve, which our undergraduate researcher Woody Hulls kindly provided. Uh, so the orange is the train the train curve, and the blue is the test curve, and the AUC is below it. The area under the curve here is below it. So you want to have these increase the AUC as much as you can for binary classification. This is sort of specific for the binary classification task. But if the test set is not as good as a training, that means you've overfitted, i.e. your model is sort of generally underperforming how you like. And if you don't get anything, if your curves are just sort of at this dashed line, well, the dashed line is sort of the 50-50 line. It means your classifier is performing no better than, a toss of a fair coin. If you ask it, does this pulse come from a single or multiscatter? If your performance is here at the dashed line, well, when you ask it that, it's just saying, well, let me flip a coin and decide, which is not good. Okay, so we have a little bit of time left. If people have gotten that far, I'm kind of interested in doing a little bit of an impromptu contest. If you have an AUC here for your test in the train, or specifically for the test, I would like you to type it into the chat. I'm just sort of curious what people have gotten so far. If you have technical difficulties, please, of course, do raise your hand. But if you've gotten to this stage, type in your scores here into the chat. Very interested to see what happens. This is not the end plot. There's still one more plot you will make, but just for now, let's pause and see what people are getting if you've gotten that far. Or have people gotten that far? What are people still on the training set or optimizing the model? Where are people at? Can somebody give me a sense? Okay, currently training. Okay, that's good. 0.877 after 5 epochs. Okay, that's good. Well, Chan, you already know the answer. I should reiterate, this is not the only way to analyze time series data or pulse train data. You can use convolutional neural networks. You can just use straight dense neural networks, and you can use other types of models as well. So don't go away thinking that this is sort of the only way or the best way to do it. There are many ways to do this, and you know, lots of ways that are not given in this workshop or this module. So I encourage you to go do more reading because it is actually quite an interesting area of research and application. So while people are training, I'll explain what this part of the code does. So here I just create a data frame that stores the original truth values of the pulses and this thing called positive probas, although they're always all positive. But and what this does is it has the truth values originally, and then it has the probability of a positive class, which is what the neural network is going to output. And then when you have this, you can produce a plot like this. I call it a separation plot, but I don't know, it's just it's a histogram of the probabilities of the events. So for the blue events that I've labeled blue, the multi-scatter events, how well does the neural network classify it? What probability does it give it to being in the positive class, the single scatter? So since they're not single scatter, the neural network should give it a lower probability of single scatter. And for the single scatter events, what probability should the neural network give the single scatter events to being single scatter? And it does very well. The example may be a bit better because it was trained for a little bit longer and probably with some better hyperparameters. So you can see here that a lot of the multi-scatter events have a low probability of being single scatter events, and the single scatter events have a high probability of being single scatter events, which is what you want. Then you say, but at what place do we place a cut to say, okay, single scatter or not? And that's where your cut threshold is. Your threshold, you have to set that based on your problem. So at the end, you should produce these two plots, this probability separation plot and the ROC AUC. And then for our little impromptu competition, I hope people are getting some numbers here that they can type into the chat. Don't be sad if there are low numbers. It's fine. You're experimenting. It's your first time. If you've got a low number, great. If you got a higher number, great. But everything is okay. There's no shame here. We're all just having fun and learning. So if you've test 0.79, train 0.80. Okay, not bad, not bad, not bad. Little bit of overfitting there, but not, I'd say probably negligible for this exercise here. And after Zacharias, after how many epochs was that? 15 epochs, okay. And the time per epoch, did you change your runtime from TPU to GPU or CPU? That should perhaps change the time per epoch. So if you want to see your time per epoch, you can scroll up. Should be here, 9 seconds per epoch. Well, that's what I had. You may have something different. – 14 to 17 seconds per epoch. Okay, good. So different things can affect that, like the hardware you're running on, the amount of data that you have, the learning rate, how large your network is. So all of these things can affect the learning and the time for learning, or time per epoch rather. Right, and this is indeed a shared resource, so perhaps that may be affecting people. Anyone else care to type in their results? Once you have these plots, that is the end of the exercise, and you can oh, I see. Yes, it may. Although that large of a penalty, I'm not sure. But so this is the end of the exercise. Once you have these plots, I would like to see people's results, some perhaps some AUC numbers. But if you have any questions, or please feel free to ask, or you want to skedaddle, please do. This is completely up to you. Does early stopping callback stop the training after a given number of bucks, no matter what? Yeah, I think up here I set it to just simply stop after five, no matter what. You can write custom callbacks that have that are more detailed, like if the if the validation loss doesn't improve after five epochs, you can have that. But I think this is just simply just stops after five. My rule of thumb, if I'm training for a large number of epochs, like 500, my rule of thumb is like 10%. But that's just my rule of thumb. But again, you can write your own custom early stopping functions. You don't have to use the pre-cooked ones. There's a question. The AUC is 0.5. Is there a specific issue that causes this? Um, I'd have to look at the specifics of your code. Um, I mean, it could be such that your model is just, it's not, I mean, that means your model is not learning anything. Your model is perhaps not sufficient. There's not enough hidden layers, not enough. For example, that could happen if you just have an input and output and it doesn't learn anything. Um, but it's sort of dependent on the model and how you train it. So you should just let me just type in here since people should already be here. So Anas, you can try and copy your function to the chat, but I'm not sure. And if I mispronounce anybody's name, I apologize. So having what I have here in the example should give you something reasonable in terms of performance. So the only part of the code that you should change is the build model part. You shouldn't have to touch any of the other parts of the code. That's a general comment to everyone. That should be right. Okay. Yes. Okay. I see the problem. Okay. So there's a difference in the activation function for the hidden layers versus the output layer. The output layer is what you want for your classification task, and it's going to be different for this case. It's going to be different than what you have in the middle. So I suggest not using the ReLU for your output dense layer with one neuron. You should use something more conducive to something for binary classification. In fact, I've given the answer here. I think that's your problem. If you think if you change that, you should get working. And let me know if that change works for you. How far along is everybody else? Okay, it works now. Oh, good, good. Got some good results. Very nice. Yep, that looks good. Okay, good. See a little bit of improvement there. So we're in the final 10 minutes now. So if you're getting to the point where you have some answers, please do post them. And if you have any final questions, please do ask them. Is anybody trying anything kind of different, like removing the convolutional layers or removing the dense layers or anything like that? Or if you remove the dense layers, yeah, I should remove, these three lines. But it's just wondering if anybody has tried any has sort of departed from the template at all. Nope. Anybody still training? Oh, is there a question in the Q&A? Did I miss one? Oh yes, okay. I saw that one. Answer that one earlier. Okay, yeah. Okay, so this is the last 5 minutes. I'm gonna sort of stop here and just ask if you've got any. There was another question. How to deal with the uncertainties in deep neural network model? Is the rock curve a possibility? Right. So dealing with uncertainties in machine learning and neural networks is it's definitely a thing. And it's a little bit of a complicated answer outside the scope here. You don't usually the rock curve is not really the metric to do that, and it kind of depends on what your task is. I mean, this gives you a probabilistic answer here, but this is only for a classification. If you're doing something like regression, which means instead of trying to predict a class or class probability, you're trying to predict a continuous value. So if you're trying to predict the tail length of a dog, for example, you can get a bunch of predictions for your test set and you have a distribution. This gives you a distribution, and you can find the uncertainty on that distribution or those distributions like that. If you're doing a regression problem rather than this classification problem. But there are ways to handle uncertainties, but they're not so easily discussed. At least the ways that I sort of understand are not as easily discussed in this course, in this module. But it's an excellent question. It frequently comes up as a topic of discussion in several projects. Right. So the question is, what is the purpose of using patience? So, yep, patience is just what that's in the context of the callbacks. So, for example, in if you use the early stopping, it just stops after 5 epochs. So I have 5 epochs here. I set it to simply stop after five, or well, I okay. So a little bit of confusion. I set it to number of 5 epochs here, so it's a little confusing on my part. But for example, reduce learning rate on plateau, patience 5. What does that mean here? It monitors the validation loss. And if it does not see any improvement of the validation loss after 5 epochs, then it will reduce the learning rate by this factor down to a minimum of this factor. So it's just the number of epochs that you wait for a certain action to happen. That's what patience is in a nutshell. So we're in the last minute. I'll ask for any questions, or you want to post your results here, or if you're having trouble, well, and so you can email me. If they're on, wait 5 seconds for any questions or results. If not, I will ask if Professor Gateskill has any final remarks. Uh,
Just simply that we will be starting up again an hour and a half from now, so it's 2 p.m. Eastern. Um, so please join us then. It'll be we'll be discussing NMR analysis data, so that's going to be a very different, again, a rather very different sort of physics scenario. So I hope you'll again be able to get a lot out of it, yet another sort of scientific application. Thank you.
all right. And with that, I will close the session. We will close the session. So thank you for participating. I hope you've taken something useful away from this. And any questions, please feel free to email me or anyone on in our group. Okay.
Sean, thank you very much. It was extremely instructive.
Thank you.